In example 10.2.1, we observed that the vector v with these three components 1, 1, 1 in the vector space R3 can be written as a linear combination of vectors in the set S in various ways. For example, v is equal to v sub 1 minus v sub 2, or v equals to 2v sub 1 minus 3v sub 2 plus v sub 3. Let's check the first one. The next theorem tells us under what condition this representation is unique. Theorem: uniqueness of basis representation. If S be the set of the vectors v sub 1, v sub 2 all the way up to v sub n is a basis for a vector space V, then every vector in V can be written in one and only one way as a linear combination of vectors in the set S. Let's try to prove this theorem. The existence portion of the proof is straightforward. Since S is a basis for the vector space V, S must span the vector space V. Thus, an arbitrary vector V in the vector space V can be expressed as shown in the equation 1. For some scalars c sub 1, c sub 2, all the way up to c sub n. To prove uniqueness, we assume V has another representation, as shown in equation 2. Let's assume that V can also be written as the linear combination of the vectors in S, as shown in equation 2, for some scalars d sub 1, d sub 2, all the way up to d sub n. We want to show that the corresponding coefficients in these two equations are equal, namely c sub 1 equals to d sub 1 C sub 2 equals to D sub 2, and all the way up to C sub n equals to D sub n. Thus, the uniqueness of the presentation will be proved. To show that, we subtract equation 2 from the equation 1, and we obtain this equation. Since S is linearly independent, so the only solution to this equation is the trivial solution, namely the coefficients are all equal to 0. Which means that C sub I equals to D sub I for all I, 1, 2, all the way up to n. And the vector V has only one presentation for the basis S. So we proved that a vector V in a vector space V can be written as a linear combination of the basis vectors in one and only one way. Theorem: if S is a set of n vectors, and if S is a basis for a vector space V, then every set containing more than n vectors in V is linearly dependent, hence cannot be a basis. So this theorem tells us that if a vector space has a basis of n vectors, then any other set containing more than n vectors in it must be linearly dependent, which cannot be a basis. To see the proof, please consult your textbook. Question: is the set S a basis for R3? Answer: no, because in example 11.1.1 we found that one basis of R3 contains 3 vectors, namely the standard basis of R3 contains 3 vectors. Since this set S has 4 vectors in it, it must be linearly dependent. Hence, this set S is not a basis for the vector space R3. Corollary: if a vector space V has one basis with n vectors, then every basis for V has n vectors. In other words, if a basis for a vector space V has n vectors, then every other basis must have the same number of vectors, but not necessarily the same vectors. Let's see the proof. Let's take S sub 1, the set of vectors u sub 1, u sub 2, up to u sub m, and S sub 2, the set of vectors v sub 1, v sub 2 all the way up to v sub n are two bases for the vector space V. We want to show that m equals to n, namely the number of vectors in the basis S1 is equal to the number of vectors in the basis S sub 2. Since S sub 1 is a basis, then by the theorem we proved just a moment ago, 11.1.2, S sub 2 cannot have more than m vectors. That is, n has to be smaller than or equal to m. By a similar argument, since S sub 2 is a basis, by the hypothesis, the set S sub 1 cannot have more than n vectors. That is, m has to be smaller than or equal to n. These two inequalities prove that m equals to n. The proof is complete. So we proved that if a basis for a vector space V has n vectors, then every other basis for the vector space V has the same number of vectors.